Alright, in this video we're looking at inverse functions. So inverses are kind of familiar in mathematics. You have plus being the opposite of minus, you have times being the opposite of divide, you have squaring being the opposite of square rooting, you have something like an exponential being the opposite of a log, you have something like sine of x being the opposite of inverse sine of x. So those are all examples of inverse operations. We're going to be talking about inverse functions, which are pretty similar concept. So something like x plus 3, for example. Well, basically what we want to think about is f being a function. It takes in an x value and it spits out an f of x value. So if we think about plugging in 4 to this function, it will spit out 7 because the function adds 3 to it. If I think about plugging in 10, it will spit out 13. If I think about plugging in 18, it will spit out 21. So what should the inverse function do? It should take something like 13 and spit it back to 10. It should take something like 21 and spit it back to 18. So f inverse of x is going to be x take 3. So if you want, you can also check if we compose f with its inverse, we'll see what happens. So this is going to be f of x take 3. What does f do? It adds 3. So you're going to get x take 3 as the input and add 3 to that. You get x. It's also true that if we look at f inverse of f, so that's going to be f inverse of x plus 3. What does f inverse do? It takes 3. So we take our input x plus 3, take 3 away from it, and you get x. So this is something that's true in general about functions. They satisfy this really nice equation sort of thing. F of f inverse of x is x, or f inverse of f of x is x. Basically, if you compose f with f inverse, you get back to whatever you started with. Some other examples, we've got 2x, so if we plug in something like 4, we get 8. If we plug in something like 10, we get 20. So we'd want to go in reverse of that. F inverse of x is actually half of x, just like that. And if we have something like e to the x, it's log of x for that one. Now, I will show you a general process for finding inverses. You don't have to just sort of know, but intuitively, this is how it works. So let's talk about functions. We had something called the vertical line test, and that tells us, is it a function? So something like this first graph would fail the vertical line test because it hits it in 3 spots. So it is not a function. Something like this one. This is a function. And something like this one, it is a function. Now, we've got another test called the horizontal line test. And that tells us, does it have an inverse? So if it has an inverse, it has to be a function and it has to pass the horizontal line test. So it sort of has to pass both tests here. So if we look at these graphs again, this one, whether or not it has an inverse, well, it can't have an inverse because it's not a function. This one here, does it have an inverse? The answer here is no, because it does not pass the horizontal line test. So for example, if we plugged in, let's have a look at 3 for the x value, and let's suppose that the y value was 5 or something like that. It is true that if we try to plug 3 into our function, we get 5. But also, this point over here at -3 would give us 5. So you also have the situation where -3 into the function gives us 5. So if we try and work out f inverse of 5, it has to both be 3 or minus 3. And we don't like having it be two different things, so that's why you can't have an inverse, because we couldn't decide whether it was 3 or minus 3. This last one does have an inverse. Now, we have a special name for whether it's got an inverse or not. So we say, if yes, then the function is 1-to-1. And another word for this is injective. So yeah. Now this one here, you could sort of calculate an inverse function, but we don't like to do that too much because it wasn't an original function to start with. So just be conscious about that example there. Okay, now here's actually calculating inverse functions for real. So there's a bit of a process here. What we're going to do is we're going to start with y is 2x plus 1 over 4. And basically, what you do is you swap x and y. So we're going to get x is 2y plus 1 over 4. So we're swapping x and y, and then you just rearrange it. So we're going to get 4x is 2y plus 1. We're going to get 4x take 1 is 2y. So that tells us that 4x take 1 all over 2 is y. Now that basically just tells us what the inverse function is. So this is the actual process for calculating it. So it's 4x take 1 all over 2. Cool. Now we can actually have a look at this on Desmos. So we've got the original function graphed sort of here. It's that red line. And the inverse is the blue line. Now, really importantly, if we have a specific point on this, like if we've got 0.25 and 0, then on the inverse function, you should be able to find that point with flipped x and y values, 0 and 0.25. Similarly, here we've got minus 0.5 and 0, and you get 0 and minus 0.5. In fact, the whole graph is just a reflection in the line y equals x, perfect mirror image over that line. Okay. One thing I should also mention is that you can do things notation-wise, like f inverse of 3 would be like 4 lots of 3 take 1 over 2. So it's just a number that you can calculate. So that's going to be 5.5 there. And what that would tell you is if I want to look at f inverse, which is the blue line, and I want to look at when that's equal to 3, then we should get 5.5 for the y value. That also means that if I plug in 5.5 to the original function, there, I should get 3 for the y value. So what that tells you is that if I plugged 3 into f, I should get 5.5. And also if I, went back with f inverse of 5.5, I should get 3. And I'm hoping you can see why they need to pass the horizontal line test for it to be an inverse. Now, f of x equals x squared. So let's go through our process. We're going to go y is x squared. We're going to rearrange it to x and y are going to swap. Now, then I'm going to rearrange for y. So I'm going to change this to y squared is x, and then y has got to be root x. So if we try and do the inverse function, now we can just write out what we had on that right-hand side of root x. So let's see what this looks like. We've got x squared. So that's this original function. And then we've got root x. And we can see that quite beautifully it has mirror imaged across the green dashed line. But you might be spotting an issue with this. This is not the whole function. You can see that I've tried to find the inverse. And if I wanted a mirror image of that red line, where the heck is the bottom half? Now, this original function did not pass the horizontal line test. So basically, what we've done here is a little bit wrong. No inverse exists, as f of x does not pass the horizontal line test. If it did, we'd do something like this. Now you might be wondering where you get the other half of it. So this bit here, this is the inverse of x squared when x is greater than 0. So if you restrict the domain of the original function, so if I look at x is greater than or equal to 0, I get that line, and then root x is an inverse of it. It works out perfectly. Mirror image across that green line. But I can't get the inverse of the whole thing. If you did want the inverse of the other half, it would be minus root x, and then you would sort of get the mirror image of the whole original function there. Probably doesn't help that that's in red, but there we go. So that blue line is an inverse of the original thing, but you sort of have to do it in 2 pieces. So we don't like that for inverse functions. Okay, e to the x, we're going to start with y equals e to the x. So we're going to swap. We're going to get x is e to the y. And we're going to rearrange for y. This is pretty one-step process, so we get log of x is y. So if we want, we can write this as the inverse function. F inverse of x is log of x. And we'll see what happens here. So turn off those other graphs. I've got e to the x here. That's that lovely line up there. And we've got log of x there. And you can see they are a reflection in the line y equals x. Here, 1 over x plus 1. So we're going to start by swapping x and y. X is 1 over y plus 1. And then we're going to rearrange. So you're going to get y plus 1 is 1 over x. You can swap these 2 bits here. It's like an algebra thing you can do. And then we can just subtract 1. So y is 1 over x, take 1. Okay. Now, if we look at this, those are the 2 original graphs. It looks a bit weird, but they are mirror images. And if you find this point like 0, 1 on the red line, we should be able to find 1, 0 on the blue line, which we do. Y is sine of x? No. So it's not 1 to 1. Therefore, f of inverse of x does not exist. And if we want to check that, we can have a look at the graph of sine of x. And there it is. Now, you might be thinking, we do have inverse sine. You've got, well, Desmos likes to call it arc sine, so be aware of that other notation, but that's just sine inverse. And it does sort of look like it's doing the right thing, but we do have to restrict the domain of the original function. So if I restrict the original domain to minus pi over 2 is less than x is less than pi over 2, then they should be inverses of each other, which they are. And that little piece of sine does pass the horizontal line test. So yes, f inverse of x is arc sine of x. Cool, so that's all good. Now be aware that when people came up with arc sine, they sort of had to make the decision to pick this piece of the sine function to do the inverse of. It could be that you wanted to do a later bit of the sine function, which was still passing the horizontal line test. So maybe you could have done the inverse of pi over 2 is less than x is less than 3 pi over 2 and done the inverse of that piece. We never ever do it like that, but be aware that when inverse sine was defined, we really did have to make a decision about which part of sine we're cutting out to do the inverse of. So inverses can be a little bit messy in that way.